Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. And right now we are in subsection 2.3.5, an example of proof by induction. Okay, so we're going to be looking at an example. And remember what we're doing. We're trying to establish that a whole chain exists of implications and that the first guy in the chain is true. So throughout, I give some reading and tidbits which kind of help us think about the mechanics of what's happening within the power set and how to think about propositions below to above and what that means in making implications, or even thinking about this conditional statement and showing that this conditional statement is true, which would mean this right here, that we have an implication. Kind of discuss this little diagram. This is 0 meaning false, 1 meaning true. This is what happens when we merge everything to either true or false. Okay, so here we go. The two ideas of saying, so we're trying to show, in this example, we're trying to show a whole lot of propositions are true. They're all indexed by all at the same time. They're indexed by the natural counting numbers. The idea is to reduce the problem. Reducing the problem, how? By establishing the chain. Because when you establish the chain, once the chain is established, actually solving the problem is so much easier, because the statement we want to prove is right here, what I highlighted in blue. But if we make a chain, this is interesting. The first guy in the chain is actually the result of ANDing all of these guys together. Why is that? Because what does the AND symbol mean, or the meet symbol? It means to take the biggest thing below everything in the arrow structure. Well, the biggest thing below everything in a chain is the first element of the chain, which means ANDing everything is the same as the first guy, which means the truth or falsity of the first guy is the same as the truth or falsity of the whole of everything in the chain. So establishing a chain actually makes this equality hold, which reduces the problem so nicely, so that knowing that all of these are true is the same thing as knowing that this is true. Doesn't this look a lot simpler than that? This is a reduction of the problem. If you establish a chain, you've actually reduced the problem. And then to solve the problem, you just look at the first guy and see if it's true or false. So let's see how we're going to do this. Now, the statement that we're trying to show is actually that all of these guys, this is the statement A sub n, that all these are true for any n. We can go back and look and see what that actually looked like. This right here, we want to make sure that all of these statements are true, no matter what for n, no matter what n is. This is the statement that if we add the numbers 1 plus 2 plus 3 all the way up till n, this is the formula for that. Now we could see this in various other ways, just a little tidbit. The average of all of those numbers 1 through n is actually the same as the average of the first and the last. So you see n plus 1 over 2, just that part right there. That's like the average of all the numbers, and you multiply by n and you get the sum. Okay, now that type of proof is not a proof by induction, yet this example, if we go and look at how to prove this statement by induction, this is a good example for actually how to use this technique. So if we look at, this is the original statement A sub n, and we're going to do some things to this statement to make some implication arrows using the assumptions of what we can do mathematically with an equation. We can add the same thing to both sides, so we can get, and then rewrite that, like rewrite this statement in terms of summation notation, because k will go, now it doesn't just go to n, it goes to n plus 1. If we want, we could put that into this notation here. We can add fractions, thinking of this as n plus 1 over 1. We can add fractions here. So these are basic mathematical things we can do. So what we've done is we've just established an implication from this statement to this one using some facts, adding the same thing to both sides. Now, why did we do that? Well, adding n plus 1 to this side made this look a lot like this, which is part of the statement a sub n plus 1. Because this is the statement a sub n plus 1 right down here. If we just think of n plus 1 going in where n was in this statement. Okay, now we can further, we can expand and factor and then rewrite, and we end up getting this. All right, so it naturally goes, so we can do mathematics to this equation and keeping it the same equation to keeping it as an equation, and we end up getting this one, meaning that a sub n implies a sub n plus 1 for an arbitrary n. So we just did this where n was arbitrary, and it could be anything. It could be 1, 2, 3, 4, 5, 6, 7, or just whatever. So what we've done, which is beautiful, by letting n be arbitrary, what we've actually done is shown that we have this arrow everywhere in the whole, we have the whole chain. This little argument shows that the whole chain exists. We have the whole chain works. So now the problem is reduced to a sub 1. Just need to check that it's true. We plug in 1 for n, and we see that it is true. So therefore, we have just shown, proved that this formula holds by induction. We just need to do two things to prove something by induction. Prove that there's a chain, and prove that the first guy in the chain is true. That is a proof by induction. It's a non-constructive proof because it doesn't construct something for us. We have to already have the construction, and then we use this technique to prove it, perhaps. So we already have the vision when we use this type of proof. So this type of proving does not actually give us new results or help us see new things. Instead, or give us intuition or insight or anything, really, all it does is it helps us to be able to know for certain that something we already think is true, and it is an accurate way and a powerful way of proving an infinite number of things in just 2 simple steps. Okay, so that concludes this little subsection on proving something by induction. Thanks for watching.